Okay, good afternoon. Finally, it comes to my presentation. I'm Mengtian. I'm a Cohort 2 Future Roles Fellow in Digital Twins. Today, my presentation topic is prototype aligned open vocabulary detection framework binding SAM and LLM-guided prompt segmentation. So this comes from research in collaboration with ARU, Anglia, Ruskin University, and we work in European Horizon project on sustainable drainage design. We aim to use the remote sensing imagery to extract the information of the geometry of drainage roads and different other elements, and try to extract the patterns from the existing design and develop new generative design for the future drainage. Yeah. So in this presentation, I will start with the motivation of the research problem we tackled and the proposed solution. And following this, there will be a detailed explanation on the four modules of the proposed methods. And afterwards, we will provide an experiment evaluation and the conclusions. So why we need to do remote sensing imagery detection? Actually, for very large-scale infrastructure management like drainage or road networks, remote sensing imagery is a very crucial result for extracting the existing as-built data, such as roads, drainage, and buildings. And it can be used for urban planning, land use mapping, infrastructure monitoring, like detecting the growth of vegetation, and yeah, of course, the digital twin updating. And the current challenges for remote sensing imagery lies on that the existing detection models are heavily relied on costly manual annotation. Like a convolutional neural network, you have to label thousands of images. And this is very time-consuming. And moreover, there's a problem of domain shift. That means if you only label on this data set and this remote sensing data set are captured only in one countries like UK or US. But if you're going to shift your models to other imagery data set, like in our countries or other different scales of cities, the detection models might not be worked. And although currently there are some existing pre-trained models like SAM or CLIP that can be used for detect the remote sensing imagery in an unsupervised way. But they are mainly designed for nature images. That means the photos we captured through cameras, but not remote sensing. And one last thing is that there's a limited explainability in the existing methods. That means we only know the detection results, but we don't know how the model makes the inference. To tackle these challenges, we proposed a new framework combining the SAM and LLM for an explanatory detection over the remote sensing imagery. First, we input remote sensing images. And the second, we use a SAM, that is segment anything models from Meta. It can segment the images, any images, but with no semantic labels. As you can see in this image, it segments objects with similar colors or geometries, but we don't know who are them. But there's one problem is that the segment anything only yields the models and the detections with many tiny pieces, but they are not connected. If we want to extract the road geometry, we want the continuous alignment, but we don't want each piece to get over there. So in the second stage, we use SAM to refine the mask, which I will explain later. And in the third models, we use LLM to generate the prompts and use these prompts to measure the similarity between the image embeddings and the text embeddings to classify what types of each segmented image piece from the same. And in the first models, we apply the alignment for taking the results from the text embeddings and image embeddings together to classify. And at the last models, we use the branch contribution analysis and the SHAP token attribution to explain the results from the detection models and allows the users to understand how the model makes decisions. Let's now go to the detailed models. So the second model is based on SAM. So as I just said, the originally SAM models would only produce the segmented pieces from images, but they are fragmented. So here I use guided prompts and some traditional computer vision techniques like the color filters and grayscale filters to connect the pieces that have the similar vision features together. Like, for example, if there are road segments, these methods can connect these segments into a whole road alignment. And the second model, which is the main contribution of this study, which lies on using large language models and clips. We first use clip, which is commonly used image embeddings that in ChatGPT or other large language models. We embed these images into image embeddings, and we use LLM such as ChatGPT to digest these images and generate semantic descriptions of these segmentations. For example, giving image piece, the large language models could describe that this image is a dry farmland or shadowed buildings. And the generated semantic descriptions are compared with the text with the image embeddings, and the image embeddings are paired with the text embeddings based on cosine similarity. And one other main component is that we use the visual prototypes. So why do we use that? That is because if we're going to adapt this method to new domains, we want to have a few examples to show what what's the new labels look like. So normally we have one image for one labels, and we also compute the similarity between the segmented image embeddings with the prototype embeddings to generate a score. And eventually, these two scores are aligned using ViPMoG, which are scaled and shifted to the same scale, and they are added to derive the final classification. And the last module is explanatory decision making. There are two main components in the explanatory modules. The first is branch contribution analysis. So this part allows us to understand in the final decisions what parts of the modules makes the main contribution. Like for this one, the prototype branch contributes this part, and the text branch contributes to this part. So we have better understanding of how the classification comes from. And the other part is SHAP, token attribution. This allows us to understand in the text embeddings which part of the tokens. The tokens are each words in the generated semantic descriptions by large language models. So based on this, we know which words contributes the most to the classification. To evaluate the proposed method, we use a data set called LLM-Day, which is remote sensing imagery, mainly on street views and rural areas. And it contains 1,600 images covering 7 classes like buildings, vegetations, drainage, rivers, and we prepare the dataset in this way. First, we take the 5 images for visual prototypes, and we use 100 images for the calibration models. And the remaining 1,500 patches are used for training-free validation. So then that means we don't use any training data. And the framework we used is the SAM, VITH, and the CLIP, and the GPT-4o. And we use a matrix of MIOU, FWIOU, which is a weighted IOU that considers the distribution of data samples across different classes, and also the pixel accuracy. That means for each pixel, we evaluate whether it predicts the right class or not. So here shows a brief summary of the evaluation results. So for MIOU, the overall score is 24.03. The FWIOU is 32.04. So that means the model generated better results on the majority class, and the pixel accuracy arrived to 64%. We also have done some ablation studies, and the results highlights that the two-stage SAM refinement significantly improves the road continuity because we connect the segments together. And the LLM prompt expansion significantly enriched the remote sensing semantic descriptions. If we only use the originally labeled text, the performance will dramatically drag down. But if we add the semantic description generated by large language models, we find that the performance is increased. And at last, the prototype ViPMoG quite improves the cross-domain semantic alignment. If we put these samples in the method, we find that the accuracy is improved. And the explainability analysis shows that the branch contribution can allow us to understand which part of the components contributes the most. And the shape analysis let us to understand which tokens in the semantic description contributes the most, like the road, forest. Gradually, we understand which words is more important than other words. And we observe that the prototype cues and text semantics form the primary decision basis this from the explainability analysis. Yeah. In conclusion, in this study, we contribute the training-free open vocabulary segmentation framework for remote sensing imagery detection, which are mainly used for infrastructure management. There are two-stage SAM refinement and LLM prompts to provide more semantic context for the detection models. And our explainability analysis allow us to understand where the decisions come from. There are several limitations. We find that the model is still struggling for very similar cars like water and barren. They have the same color or same textures. And the prototype presentation is still constrained by the small prototype library. So in the future work, we plan to expand the data set, and we will try different data set to evaluate the ability for cross-domain adaptation. Yeah, so that is the end of my presentation. I would like to acknowledge the founders.